Hey class, Mr. Bean here for Honors Physics. This is going to be video 44, and we're going to include topics of little g, your weight at the equator versus at the pole, and how to find the mass of a planet, as well as some simulations. Okay, so let's go and take a look at part A here, which is called little g. All right, so little g. So far in class, we have described the value of little g. Hold on, let me, I'm going to use a black here. We decided that little g has the value of 9.8 meters per second squared. So the question is, where did this value come from? Okay, where did it come from? Good question. All right, so in order to answer this question, we need to go ahead and take a look at the Newton's law for universal law of gravity. So what that says is that here's force, right? And we have here, of course, big G, okay? We have, we'll use the Earth. We'll say this is the Earth here. We have the mass of the Earth, right? And we have the mass of some person, okay, maybe mass of some person, and divided by the radius squared. Okay. All right. So since we're talking about the Earth, what does that mean? That means, let's take a look here. Here we have a person standing here on the surface of the Earth, okay? And what is this R value? So this R value, let's go ahead and maybe use green. So this R value, here's the center here. So this R value is going right to here. This would be R, or the radius of the Earth, okay? Now the Earth is not quite a perfect sphere, but we'll assume that it is for this discussion. Okay, all right, let's go back to black now. All right, so here we have, and this is the mass of the person here. And of course, this is the mass of the Earth. Okay, right here. Okay, so what is this little g here? Well, if I go up here, if I were to just take a look at this right here and kind of draw an arrow here, this is called little g, or the gravitational field strength. So little g has the value of big G, or it's made up of big G, the mass of the Earth, right here, mass of the Earth, okay, and mass of the Earth, G, mass of the Earth, and also the radius of the Earth squared. Okay, so that's what little g is. Okay, and so that's where it comes from. Okay, and this is where this value here comes from as well. Okay, now take a look at this person here. Okay, he's at sea level here, and let's say we have another person over here, and they're standing here, let's say. Okay, all right, so on the surface here, the g value here is 9.8 meters per second squared near the Earth's surface. But what about here? Okay, what about this location here? Okay, so if we do that there, let's go ahead and just do some different colors here. I'm going to use green. So again, from here to about the edge would be the Earth's radius right here. That's the radius of the Earth. Now we have some altitude here. Okay, we'll go ahead and maybe use pink here, and this here is the altitude A. We'll call this the altitude. Okay, so looking at this here is obviously the altitude plus the radius of the Earth is bigger. Okay, so if I go over here and I were to, let's say, what's the G, and maybe this, we'll call this what's the new G here? Okay, so this, maybe we'll call it G prime to differentiate it. So you have a big G here, right? The mass of the Earth does not change. Okay, that's still the same. But now what happens is that we have to include the radius of the Earth, right? Radius of the Earth plus the associated altitude. Okay, and this got to be squared. Okay, so in this case here, this is getting bigger. That means G prime gets smaller. So if I was to compare this, I could say that the gravitational field strength at the surface is going to be greater than the gravitational field strength at the top of the mountain here. Okay, so the further you are away from the radius center of the Earth, less the gravitational field is less. Okay. All right, now back over here again. So here we have force, right? And we're going to go ahead and replace it with little g. And this is the mass of you or a person. So when we look at this, normally we would call this weight. Okay, what is your weight? So there is G and this is M, or we like seeing mg is what we're used to seeing. So when somebody asks you how much do you weigh, what they're really asking you is what is your gravitational field, or what is your gravitational force of attraction to the Earth? Okay, all right. So this is, an idea of where little g comes from. But still, where does the 9.8 come from? Well, if we go down here, it says here, try to calculate the gravitational field strength on the surface of the Earth using the knowledge that the mass of the Earth is about 5.98 times 10 to the 24 kilograms. The distance from the surface to center mass of the Earth, it varies because Earth is in a sphere, is about 6,378,000 meters. I plug all these values in, and lo and behold, we get 9.8. Okay, all right. So, uh, uh, so gravitational field strength depends on the mass of the planet you're on, and also the distance you are away from the center. Okay. Now, another question that comes up is, how do we know what the mass of the Earth is? Okay, that's going to come up in the next topic coming up here. All right. So right now, I'm going to hit pause, and let's take a look at the gravitational field sim. Okay. All right, so let me get rid of this here. All right, so here we are back again here, and here we have a simulation here called calculating gravitational field strength. All right, so here we have a satellite with a mass of 1479 kilograms. Okay, it's placed at an altitude of 72,300 what does it say, kilometers above the surface of Saturn. Okay, so we're on Saturn here in this particular example here, Saturn. Okay, and question is, what is the strength of the gravitational field at this location? Okay, all right, so we're at Saturn. Okay, so we're going to have some questions here for you to ask. Okay, the first question is, what is the mass of the satellite? Okay, and what is the altitude of the satellite? And what planet are we on? Okay, all right, so let's go ahead and go down here and let's find out it's Saturn, right? Okay, we're down here. Here is Saturn. So at this location here, go ahead and record the mass of Saturn, the radius of Saturn. Okay, we need those two. Okay, all right. Let's go back up here. So using the equation that we just used, go ahead and try to calculate the gravitational field strength at this location. All right. All right, Thanos did this problem, and Thanos' answers were good. Okay, so the actual field strength was 2.15 newtons per kilogram, or you can simply say 2.17157 meters per second squared. Okay, I got 2.24 meters per second squared, so we're pretty close. All right, so that is a gravitation. All right, so now on to part B. It says here, does your weight differ at the equator versus the poles? Okay, good question. So let's take a look here and kind of see what's going on before we start the problem here. Okay, so here, if you're here, you have the normal force, which is the scale acting in the upwards direction here. And you have your weight, which is mg, acting downwards. Okay, now here, when you're at the equator, you have the scale going in this direction here, which is the normal force, right? And then now it's rotating on this axis right here. So you have weight, which is going in this direction, okay, which is mg right here. This is mg. And you have centripetal acceleration also acting in this direction. Okay, so those are some things to consider. So there is centripetal force acting here. Now, I want to go ahead and use green here to talk about the radius here. So let's take a quick look. So if I'm at the equator here, this is R. Okay, R is pretty long. As I move up the latitude here, R begins to get smaller and smaller. Okay, we'll go up here, right here, and then finally at the top. Now, at the very top, at the North Pole, R, the radius, is going to be 0. Okay, so let's see how this all plays a part in determining whether you weigh more or less at the equator versus the poles. Okay, we'll do our analysis here. Okay, first of all, we'll go ahead and start with sum of the forces, okay, is equal to m times centripetal acceleration. Okay, and this person here we'll say has a mass m, and the same person up here, mass m. Okay, so the centripetal force. So let's take a look at the equator here. Okay, so we have, we'll say going up is going to be positive, and the centripetal acceleration, as well as the weight here, will be negative. So we'll go ahead and put that in. So we have here the normal force. Okay, there's normal force minus mg is going to equal m, and we'll go ahead and substitute in the formula for centripetal acceleration, which is v squared over r, like so. All right, so let's take a look at the normal force, which is the scale. Okay, take our time here, and this is going to be mg here, right? Oh, I almost forgot. Since acceleration is negative, this also has to be negative here as well. So we can't forget the negative sign. So it's mg minus m v squared over r. Okay. Just make sure that because weight is negative in this direction, the centripetal acceleration is also negative. So that's where this negative sign here came from. All right. So now let's go and take a look at this formula here, and take a quick look at this and say, if the radius begins to get smaller and smaller, and the radius is 0, we seem to have a division by 0 situation here. However, if you remember the Grogu or the Baby Yoda and Ahsoka discussion, this is not the true formula, or it's not the expanded form, I would say. So if I do the expanded form, we have to think about that v, the speed, is equal to 2 pi r divided by t, like so. So if I were to do v squared, that would equal 4 pi squared, right? R squared divided by t squared, like so. Okay, so if I substitute this into here, what we get is the normal force is going to equal mg, right? Mg minus, right? M 4 pi squared r, all this divided by t squared. All right, so now we can see if r is 0, this term goes away. Let me get the, okay, that term goes away, leaving just mg, which is shown right here. But if there is a radius, or if you're some altitude or some distance away in terms of the rotational axis here, there is an r factor. So at the radius, so at the equator, this r is significant. Therefore, this is a subtractive effect on your weight here. So you actually weigh less at the equator than you do at the poles. Now, another question. What happens if the Earth spun faster or spun slower? Okay, well, let's take a look at scenario 1. Let's say the Earth rotated faster. Okay, we'll say rotated, rotated faster. Okay, so rotated faster, let's say. Okay, so that means, for example, let's say it rotated faster. So let's say instead of 24 hours, it rotated in 20 hours. So let's say the rotation was 20 hours. Okay, that means that the period decreased. Okay, the period decreased, the rotational period decreased. So looking at this right here, if this gets smaller, that means that this term becomes bigger. So there's a greater subtractive effect here. Therefore, the force would decrease, or your weight would decrease. Okay, let's say you rotate slower. So we rotated slower. That meant, let's say the period was, let's say, 26 hours. 26 hours. That means that the period is increasing, So if this is getting bigger, okay, this is getting bigger, that means that this term here is getting smaller. So that's a reduced, that's less of a subtractive effect. Therefore, your force or your weight would also increase as well. All right, so I hope this here gives you some insight on why you might be less at the equator than at the poles. All right. All right, so part C. How do we find the mass of a planet, or how do we know what the mass of a planet is, or how do we know what the mass of the Earth is? Excuse me, mass of the Earth is, or even the mass of the Sun. All right, so let's take a look at this. And the next unit, we're going to be getting into planetary motion. So we're going to assume that this is nearly circular, but it's at an angle to us. Okay, so some things to consider. Let's go ahead and maybe use red here. So from the center of the sun all the way to the center of the Earth, we'll go ahead and call this R. That's the radius, or the distance, orbital radius. Okay, and the Earth is spinning in this direction. So as it spins here all the way around, we know that T is 1 year, right? The period is 1 year. Okay, it takes to make one orbit. Okay, period is 1 year, and we'll call this here the mass of the Earth here, and of course we'll call this here the mass of the Sun. So we want to know is what's the mass of the Sun? So in order to use this model here, we have to assume a couple of things here. We need to assume that the mass of the Sun is much, much greater than the mass of the Earth. Okay, so that's our first assumption we have to do here. Okay, all right, so let's go ahead and kind of see how we would do this problem here. So as this thing orbits, what is keeping the Earth in circular orbit? Is the force of gravity, or gravitational force of attraction. All right, so that means that it's the force of gravity here, right, is equal, that is supplying the centripetal force, is gravity. All right, so we go over here, and so we'll go ahead and put in here, here's big G here, right, there's big G. We have here the mass of the Sun. We have the mass of the Earth divided by the orbital radius squared. Okay, that has to equal, so this is in centripetal motion here. It's going to be the mass of the Earth here. Okay, we'll say here V squared over R, like so. Okay, we'll start with this. Now, if I look closely, some things do cancel out. Mass of the Earth cancels out, or matter of fact, mass of the Earth, that doesn't even matter. This R cancels out, as does this square term. So when it's all said and done, we have here G, here's mass of the Sun, divided by R, is right here, is going to equal just V squared. Okay, now V squared, okay, remember V was, now it's nearly circular orbit, so we can go ahead and use 2 pi R, right, divided by T. Okay, therefore V squared is going to equal 4 pi squared R squared over T squared, like so. Okay, all right, so we have this here, so we're going to substitute this into here. So when we do that, let's go ahead and rewrite it again. It's going to be G, the mass of the Sun, right, over R, like so, is going to equal, here we have 4 pi squared, right, R squared is here, all over T squared. Okay, so we need to solve for the mass of the sun. Okay, so the mass of the sun, right, is going to equal, so I got to be very careful here, 4 pi squared r cubed. So here's r cubed divided by, then we'll have here g uh, t squared. All right, so in order to find the mass of the sun, we have to get this here in meters, right? Got to be in meters, and this has to be in seconds in order for this to work. All right, so this is how we would calculate the mass of the sun, mass of the Earth, or mass of any planet, provided that we have the period of rotate or the rotational or the period of revolution, and we have the orbital radius. Okay, we'll hit pause, and we'll work on this mass of the planet simulation. All right, so we'll go ahead and do this finding mass of a planet simulation here. We'll go ahead and click on begin. Okay. All right, so here we have we'll find mass of planet, and we have some information here, and it says here, click on the timer to start the orbit of your satellite. Okay. All right, so let's go ahead and we'll start the timer. So the first thing we want to do is click on the timer, and we'll see what the situation is. All right, so we'll wait for it to go around here. Okay. Okay. All right, almost done here. So let's get ready to click on the timer for stop here. And stop. Okay, so go ahead and record what the time is. All right, so go ahead and take this time here and multiply it by 3600 to get seconds and see what you get. All right, so now let's go ahead and show the question here. Okay, so we have a question here. So it says here the mass of the satellite is 147.0 kilograms. Now, does the mass of the satellite actually play a role in this calculation? Okay, we'll hit pause and let you answer that. Okay, all right. Now here we have the planet's radius. Okay, so the radius of the planet is going to be 1.7 times the radius of Haumea. Okay, Haumea. All right, so let's go ahead and come on down here and try to find Haumea. Okay, here we go right here. Here's Haumea. So go ahead and get the radius. Okay, now go ahead and calculate what the actual, okay, so get the actual radius we're going to be dealing with. Okay, all right, now let's also get the altitude. The satellite has an altitude above the planet's surface is 3622. So go ahead and get the altitude as well. And it's 3622 kilometers. So add 3 zeros to get meters. So it'll be 3622000 meters. All right, so in the next question here, go ahead and get the actual orbital radius. Okay, we'll hit pause. All right, so now that you have the orbital radius and we have the period, let's go ahead and use the equation that we just solved for to find the mass of this planet. Okay, we'll hit pause. All right, now this final last one here, gravitational force on a satellite. All right, so you have a satellite with a mass of 537 kilograms. Okay. And we'll go ahead and write that down. 537 kilograms is the mass of the satellite. And it has an altitude given of 23,168 kilometers. So we need to add 3 zeros to get meters. So 23,168 000 to get meters above the surface of Uranus. Okay, so it says here, what is the strength of the gravitational force on the satellite? Okay, so that means that we're going to be calculating the gravitational force of attraction. Okay, so some things that we're going to need to know is the mass of Uranus. So let's go ahead and scroll down here and try to find Uranus, which is right here. So we need to get the mass of Uranus, which is given as 8.68. We'll say e to the 25, okay? And then we also need to know what his radius is. So the Uranus's radius, go ahead and write r here, is given as 25,559,100. Okay, and so 25,559,100 meters, but let's go ahead and use scientific notation and let's call it 2.5 e to the 1, 2, 3, 4, 5, 6, 7. 2.5 e to the 7 meters, okay? And so let's try to use scientific notation when we can to make it a little bit easier. In fact, the altitude, which is 2, 3, let's change the altitude also to scientific notation as well. All right, so we have all this information that we need. And so now what we want to do is go ahead and use the universal law of Newton's universal law of gravity to calculate what the gravitational forces on this satellite. And don't forget to add the altitude to the radius before you square it. All right, and we'll check our answers, and that will conclude this video. All right, so it looks like Grogu got the right answer here. The gravitational, the actual was 1,307.2 newtons, and Grogu got 1,339. Well, close enough. All right, that's it. Good luck, and catch you guys later.